Hello dear students. In today's class, we will continue our discussion on MHD approximation, which is magnetohydrodynamics approximation, which is essentially treating plasma as a magnetic fluid. So, it is MHD magnetohydrodynamics, in which plasma is essentially treated as a fluid which is magnetized. So, we have defined these parameters, bulk parameters, that means they will define the characteristic features of the entire plasma: mass density, current density, mass velocity, total pressure, and this is the total charge density, right. So, using this we have derived the charge conservation equation, in which we realize that the rate of change of charge density with respect to time will be equated by the divergence of the current density, right. So, similarly, we have what we have done is we have multiplied equation 1 and 2 with QE and QI and got this expression. So, we can get the mass continuity equation, which conserves the mass inside the plasma, by similarly adding these two equations after multiplying with ME and MI. So, we can start with the equations dou by dou T of ME NE plus del dot NE ME UE is equals to 0. So, this is the continuity equation. We have multiplied the equation with ME, the mass of electron, and similarly we can write an equation for the ion MI NI plus del dot So, you must realize that in MHD approximation, what we do is we write single equation of continuity or single equation for everything instead of two fluid equations, right. So, what we can do is, now let us say we call this equation as A and this one as B. We can add these two equations, A plus B. Okay. So, we can write dou by dou T, the partial derivative with respect to time, NEME plus NIMI plus del dot is equal to 0. Or using the parameters that we have defined earlier, we can write NEME plus NIMI plus the mass density del dot number of particles per unit volume multiplied by the mass, which becomes mass per unit volume, which is rho E UE plus rho I UI is equal to 0, right. Now, we define the fluid velocity, the fluid mass velocity, as which is equals to NE ME UE plus NI MI UI divided by NEME plus NIMI, which is still in the dimensions of velocity actually, right. So, can be defined, can be written as NE ME the total density of the fluid, rho m, which is this part is nothing but rho E plus rho I, right. So, using this expression into this one, what we can write is NE ME UE plus NI MI UI is equals to um rho m. So we can write the total continuity equation as dou by dou t of rho m plus del dot um rho m is equals to 0. You see this one, this is rho e. Let us slightly change the color scheme so that it becomes easy for you to understand if you are referring directly to the notes. This part becomes rho e plus rho I, so does this part rho e plus rho I, and we are defining rho e as rho m, which is the entire density of the fluid, right. So this becomes rho e plus rho I becomes rho m here, and all of this becomes um multiplied by the denominator, right. So this is what we have here, right. So this becomes dou by dou t of rho m plus del dot um rho m is equals to 0. So um is the fluid's mass velocity, rho m is the density. So we still have the same form. The form hasn't actually changed much. But what we have done is, instead of using two equations, we now have only one continuity equation. With this continuity equation is referred to as the mass continuity equation. This equation speaks about the conservation of mass, right. So how many equations we have got now? We have got two equations, one for the charge conservation and another for the mass conservation. The other equation that is important is the equation of motion for the bulk plasma. This is equation of motion for bulk plasma. What does it mean? It means that we have to write F is equals to ma. We have to write F is equals to ma for the plasma, which is not made up of two fluids, it is only one fluid. So this is basically the momentum equation that we are very familiar with. So we can get the momentum equation for a single fluid plasma if we add both the momentum equations of electron and ion. So essentially we just have to add both the equations, so which is me ne dou ue by dou t plus the advection term me ne ue dot del times ue is equals to minus del Pe plus Qe Ne times E plus Ue cross P. The pressure force is taken into account and the Lorentz force is taken into account. So we similarly write Mi Ni. So the reason that I am writing these equations so many number of times is that by a practice you will remember these equations thoroughly. So the idea is, when I am writing these equations, you should be able to understand what does each term represent and why the terms are added like the way they are done. So the essential inference of all this mathematics is supposed to be understood, is supposed to be the context of this lecture, right. So now we have these two equations, which are basically the momentum equation for the electrons and ions, or electron fluid and ion fluid. We simply add these two equations. So we'll write this simple algebra, which is dou by dou t of MENE UE plus MINI UI is equals to minus del of PE plus PI plus NEQE plus NIQI times E QE NE UE cross B plus QI NI UI cross B. So, this is the electric field, the magnetic field. What we have done, we missed something, what is it? We missed or we neglected the convective derivative, the convective part of the total derivative, the convection term, and we have only accommodated the first term, which is the partial derivative of the velocity with respect to time, right. So, this is further simplifying it, we will write the left hand side as MENE plus MINI times dou by dou t of UM. We know what is UM. Yeah, this is UM. UM is equals to minus del of PE plus PI plus this one, the total charge NEQE plus NIQI times E plus, so this is J is equals to NEV, right, charge multiplied by the number density multiplied by the velocity. So, this is basically J cross B, so this is for the electrons, right, plus J cross B for the ions, or we can simply write it as NEME plus NIMI dou by dou t of UM is equals to minus del of PE plus PI plus J cross B, which is nothing but the idealized MHD equation for a single fluid plasma. Here we have to write this NEQE plus NIQI times E, but in an ideal case the plasma is electrically neutral and the electric field E is basically 0, which means we can get rid of this term, we can make this term to be 0. So, idealized equation for the bulk plasma, the momentum equation is basically this, right. What is the name of this equation? This is the equation of motion for the bulk plasma, right. Now, we have one more equation, which is the rate of change of current density, the final equation of MHD. So, the final equation describes the variation of current density with respect to time, which will be less. So, we can start from the momentum equation itself, which is MINI times dou UI by dou t plus UI dot del times UI equals to minus del P plus QI NI times E plus UJ cross B. So, we can start with the momentum equation itself. where it's ui, yeah, ui. So where I can be ion or electron. So probably if it is confusing, we can use a subscript of j, because I generally denotes the ion, right. What we do is we take this equation, and we multiply this equation by QE by ME and QI by MI, and then add the two equations. So I'll write the two equations again: QE NE times dou UE by dou T plus UE dot del times UE is minus del PE plus QE NE times E plus UE cross B times QE by ME. So this here on the left hand side, you may be seeing that the mass is missing from here. That is because it gets cancelled by the multiplying factor that you have, which is QE by ME. So similarly, you can write QI NI times dou UI by dou T plus UE dot UI dot del UI is minus del Pi plus Qi Ni times E plus Ui cross B times Qi by Mi. Right, we just add these two equations to get the rate of change of current density, which will be written as dou by dou T of QE NE UE plus QI NI UI is equals to minus QE by ME del PE minus QI by MI del PI plus NE QE square by ME plus NI QI square by MI times the electric field plus NE QE square by ME times UE plus NI QI square by MI times UI cross B. So what I have done, I have just go back to this, I have just added these two, took the factor QE by ME inside the bracket, and this is what I get. Now here, in order to go further, we need to impose the condition that the plasma is electrically neutral. That means the number of charge carriers of ions and the number of charge carriers of, let us say, electrons are both equal, or to say that the total positive charge is basically equal to the total negative charge. By writing this equation, we are also accommodating the provision that if the positive ions are not singly ionized, then the charge neutrality is maintained by having equal number of electrons to compensate for the effective positive charge. So the total positive charge is equal to the total negative charge. We refine the current density J as NE UE QE plus NI QI UI, and the mass velocity as NE UE ME plus NI UI MI divided by so using these two factors and this into this equation, we can write it as dou J by dou t, because you see the left hand side has the current density. Dou j by dou t is equals to minus QE by ME times del PE minus QI by MI times del PI plus NEQE square by ME plus NI QI square by MI times E plus U cross B plus QE by ME plus QI by MI times J cross B. Right. So, this is the rate of change of current density with respect to time. So, this is the final MHD equation which tells you the rate of change of current density with respect to time. So, this is the final MHD equation which gives us a rate of change of current density with respect to time, which is a single equation instead of two different equations.